Hello everyone, this is Mr. Lee. In this video we are going to go over the rotational motion unit. It has a lot of different topics, but we're just gonna get through them all. Let's begin. So the first thing that we did is we talked about the kinematics. Let me zoom in after this. The kinematics, rotational kinematics. Now nothing new here, except that we got a couple new variables that were in Greek. So the first thing that I like to do is I like to make sure that I understand the variables that I am given. So we have x, v, a, and t. And so instead of x for position, we say it's theta. Okay, and the units are radians. Instead of saying v, we said omega, and that's radians per second. Instead of saying a, we say alpha, radians per second squared, and time, of course, just time with seconds. Okay, that's my units. All right, so from here we went over the different kinematics equations, and those are the ones that you should have down in your equation sheet. Now, if you remember the kinematics equations from earlier this year to right now, the two are the same, right? So this is the translational form of the kinematics equation. It's all you got to do is you just got to get the variables, and you have to just replace the variables that you know that are direct translations, right? So instead of position, we say theta, and we continue from there. All right, so there were a total of 3 equations, and you are expected to know those 3 equations, not memorized, but to be able to go from one form of the equation to another. Now, I do have to let you know that the 3 equations that you see, you do see those on the equation sheet, but it is helpful for you to, one, be able to identify the proper equation and what the similarities are. Okay, now from there we went into the idea of graphs, right? So we did the different kinds of graphs, and once again, I like to always show it with the translational version and the rotational version. So position versus time, right? So instead of saying position versus time, we say that it's theta versus time. Now a couple of things here. Slope, remember slope is division. So theta divided by time gives you omega. All right, much like position divided by time, that gives you velocity. Okay, so the slope for this graph, whatever it might look like, that'll give you the velocity, the rotational velocity. Next up, we have velocity versus time. Now here, there's 2 things. There's the slope itself, so velocity divided by time, that gives us acceleration, and the area under the curve, which is velocity times time, which gives us displacement. Okay, and so the analogous to this, instead of saying velocity time, we have omega versus time. And the same holds true where the slope for the omega versus time gives us the rotational acceleration, and omega times time gives us the change in rotational position. And the last one is the acceleration versus time. So we have acceleration versus time. There's no slope for this one, just area under the curve. So acceleration times time gives us the change in velocity. And then we have alpha times time, where alpha times time gives us the change in omega. All right, so we have those 3 kinds of graphs. Now from there, one last equation that you need to have. I'll put this up there. And that is the translational velocity and rotational velocity equation. And the equation looks like this. We have omega is equal to the linear velocity or translational velocity divided by the radius. That's the star one. I don't think they give you this equation on the official equation sheet, and so I'm going to highlight that because you should definitely memorize that. Let's get that galaxy pen out there. Yeah, get that down there. Okay, next we have this thing called torque. So we just went kinematics, and now we're going to do the forces. So force, torque, okay, torque. Now there's 2 different versions of torque. I'm going to go over both. First off, torque. Okay, tau is equal to I times alpha. All right, now here's what you need to know about I. This is the rotational inertia, and I said this before in my videos, But rotational inertia is the most important idea behind this entire unit. You need to fully understand this idea behind rotational inertia. We said that rotational inertia mainly depends on two variables, mass and the radius, and of course that radius is squared. Now based on this shape, there could be a different number that comes in front of this mass that changes the rotational inertia. Now, the most common thing that you need to know about this, one, that you are usually given the rotational inertia for a object, and that the different shapes have different rotational inertia. Now, common type of problem that they'll give you is you'll have two objects, right? One of them will be an object called a solid disk. Okay, we have a solid disk, and then we have a solid ring. So we have a disk and a ring type situation. So with the disk, they'll say that they have they'll have the same mass and they have the same radius. Okay. Now, according to, if you just look at this, it kind of looks like if you had the same mass and the same radius, they should have the same rotational inertia, but we know that's not true. Okay. First off, this radius, what you're looking at with the radius is not just the radius of the shape. So I'll do this in a different color. Let's use yellow here. Let's see if I could do that here. Right? We're not looking at just that radius right there, but you're looking at a combination of both the radius and the mass. And so what you're looking at is how much mass is within that radius. Okay, within that square, how much mass do we have? Because if we were to compare that with something like this, I'll just do it in a different color, right? So we know that the radius is the same, but within this chunk of the ring, of the hoop, we have so much more mass compared to that chunk of the disk. Because the mass is distributed within this, there is actually less mass at the radius, versus here there is more mass, okay, at the radius. Okay, so there's a huge distinction, and so we would say that because there's more mass on the outside, there is this inertia is greater and this inertia is less. Now, with the topic of inertia, okay, you definitely need to know this definition. It is the likelihood that a force will, I guess, affect it, right? Like, that's just a very, I don't know, not a professional way of saying it. The likelihood that a force will affect it. Like, a more proper way of saying it is the how much it's likely to accelerate, okay, if a force affects it. So more inertia. Okay, so if your inertia increases, more affected by the torque. Okay, and we can say that because, of course, torque is equal to the inertia times the acceleration. So if we have an object I, and that object I experiences a torque, okay, but that inertia is super small. Okay, if it's super small, because of the way the variables relate to each other, the object will accelerate at a greater rate. So the change in velocity will be greater. So if we were to put two objects like the disk and the ring, right, on a slope, we also did some experiments with this. The less inertia, the more likely it'll accelerate. The more likely it'll accelerate, the faster it can go down. Now, the way that I phrase it is important. Remember, acceleration does not equal velocity. Okay, acceleration is a change in velocity. Doesn't mean that it's going fast, but it will speed up at a quicker rate. Much like for torque, right? The same torque, but you have a object with a greater inertia. Okay, it's going to be accelerating less. So the force of gravity, if that's the one that's causing the torque, is not going to be able to accelerate a object with a greater inertia. And therefore it won't go down the ramp as quick. Okay, so the big idea behind this one is that you're given an I, and you have to figure out what that I represents and how it's going to be affected by the torque. Now, the other torque equation, and this is the one that we did a lot of practice on, but this is the force times radius one. And usually for something like this, you're given like a bar, right, and there's like a fixed point. And like we'll say, okay, so there's like F1 here and there's like F2 there, and it'll be like, what's the net torque? what's the net torque? What is it? And in this case, you would just add torque 1, which is force 1 times the radius, whatever this radius is, right? We'll just call that R1. And then you'll add that torque 2, force 2 times the radius, well, whatever radius this is. Okay, and then you would just add the 2 up, torque 1 plus torque 2. Okay, now know that you're not usually given which way, or excuse me, you are given usually which way is positive and which one is negative, but just in case they don't give it to you, know that you can set that yourself. So for example, this F1, when it pushes down on this rod and it pivots around this area, it'll spin like so, and we call that clockwise. And you can say, okay, so anything that is clockwise is considered to be positive, right? It's completely up to you. You can say it's negative if you want. Much like here, if we have this force acting on the bar will rotate like so. And this is counterclockwise, and it's up to you. You can say counterclockwise is negative or positive, but make sure you just keep it the same as you work through your problems. All right. Okay. So if you're ever given a scenario where you're given like numbers and the radii, all you gotta do is multiply the two together, and just know that a torque. Okay. So a torque causes objects to rotationally accelerate. So that's alpha. Okay. And the reason that we can say this is because we have the two equations. Torque is force times radius and I times alpha. So what this shows us is if you exert a force on a rotating object, that rotating object will accelerate. Okay, so that's big. Right here. Start that. Highlight that. Important. Get out your Galaxy pens. You got to know this one. This is a definition type of problem. All right. Next up, we did rotational energy. Okay, we said that rotational energy, K rotational is 1/2 I omega squared. And if you ever see that an object is rotating, know that some energy went into causing that object to rotate. So I remember the scenarios that we worked off of, right? We had an object on top of a ramp, and we would say, all right, at the top of the ramp, what kind of energy do we have? It was like, oh, that's easy. That's gravitational potential energy. And as that object is rolling down this ramp, this gravitational potential energy turns into both kinetic energy and kinetic energy rotational, okay, when it reaches the bottom. But if it's like somewhere between, there's still some gravitational potential energy. So this is a big idea here, that if you have an object that is rotating, there is some energy behind that rotation. Not much more to say about that other than you definitely need to know how to set up the conservation of energy equation, much like I just showed you. All right, and the last one. The last one is rotational momentum. Rotational momentum, and that's with capital L. L is equal to I omega. Very important. Okay, I omega. Now this has a little star, a little asterisk, knowing that I is based off the mass and the radius squared. All right. So the classic problem that you will be given usually is the idea behind an ice skater, right? So when an ice skater spins around, if they have their arms out, okay, the radius goes up. If the radius goes up, the inertia goes up. Okay, so if we were taking a look at relationships, if I goes up, okay, the momentum is conserved. Momentum is conserved, and this is the conservation of momentum equation. Okay, momentum is always conserved unless there is an outside torque. Okay, unless there's an outside torque, momentum is always conserved. Okay, so if we take a look at this, if your rotational inertia goes up, that means your omega goes down, right? So if you're spinning around and you extend out your arms, you will slow down. Okay, if you we did a lot of different videos where we looked at that relationship, and the vice versa holds true too. Okay, if you have your arms out and you bring them in, your rotational inertia goes down, but your omega goes up. You actually spin faster. You need to know this. Okay, you need to know this relationship. They will test you. Now, with this idea, we have this idea behind the conservation, right? So your L initial has to equal to your L final. Now this is for any kind of system. They could say this for any two objects that are rotating, right? So one of them is the we have the planet versus the moon system, right? So we have planet here and we have the moon all the way out here, right? So for this system, if we're saying it's the planet-moon system, momentum is conserved. Okay, momentum is always conserved. So it might be moving fast, or it'll be moving slow when the radius is super far out, because we have a big R, right? If we have big R, your omega goes down. Much like here, we have your R is small, therefore your omega goes up. Okay, so it has that relationship. You need to know this. Now, if they were to say that it's just the moon system, right? It's just the moon that we're looking at. We're not looking at the planet. The planet is there, but we're not considering it part of the system. It's just the moon system. So if it's just the moon system, okay, if it's just the moon system, we can say that the moon has a outside torque or outside force affecting it. And we can say this because the rotational momentum changes, right? It speeds up, it slows down. And if we were to be asked, well, what's changing it? We'll say the planet. Well, the planet is pushing and pulling on it based on the force of gravity, right? So be very, very cognizant. Look out for how they define the system. You know what? That's a star one. The word system. So very important. All right. Yeah, so we get that. And yeah, when you're looking at the different problems, make sure that one, you are able to define the system, and two, make sure you are able to identify if there's any outside forces. If there are no outside forces, just straight up look for that answer choice where they say that momentum is conserved. But you gotta be careful because you gotta know what you're looking out for. But that is a really easy way of just trying to find the correct answer there. Okay. All right. Well, that's it for the rotational motion unit. A lot of the rotational motion unit actually just overlaps with the previous units because, you know, the ideas behind force, momentum, and energy. So if you do need to go back and look at those review videos, feel free to do so. But best of luck on your exam. Bye-bye.